Welcome to the 5th session on electrolytic conductance. In this session, we will be dealing with transport number and its determination. Now, why do you need transport numbers? This is because you can see that in certain electrolytes, for example, if I take nitric acid, we have H plus ions as well as nitrate ions. Both are univalent ions and we expect the current to be carried by 50% by H plus ions and 50% by nitrate ions. But actually what happens is 84% of the total current is carried by H plus ions and the rest 16% only by nitrate ion. Now, what is the reason for that? Here comes, that is, the conductance of H plus ions depend upon the velocity with which the H plus ion moves, as well as the conductance of nitrate ions depends upon the velocity with which the nitrate ions are moving in the electrolytic solution. So, what happens is, since H plus ions being small and due to special conductance like Grotthus conduction, H plus ion carries most of the current in an electrolyte, that is 84% of the total current, while nitrate ion being large in size carries only 16% as it moves slowly. Now, let us go in detail with transport number and its determination. Transport number or transference number, it is known by both the names. It is a fraction of the total current carried by a particular ion. That is if you are having a total current of 50, suppose the total current is represented by 50 and the fraction of the current carried by a particular ion is 40, suppose, and this comes as the transport number of that particular ion. And by this you can see that this cannot be a whole number, that will always be a fraction, and if whole of the current is carried, it becomes 50 out of 50 and that becomes equal to 1. So, the maximum value for transport numbers or transference number is 1 and the fraction carried by each ion will be, it will be a fraction which will be less than 1. So, transport number of cation, that is denoted as T plus, is the current carried by the cation divided by total current passing through the electrolyte. Similarly, transport number of the anion, that is T minus, is equal to current carried by anion divided by total current passing through the electrolyte. Now, we all know that the current carried by a certain ion is directly proportionate to its velocities, and therefore, we can put it as T plus, that is the transport number of the cation, is equal to U plus, that is the speed of the cation divided by speed of cation plus speed of anion. Similarly, transport number of an anion is equal to speed of anion divided by total speeds added up, that is of the cation and the anion. Now, as said earlier, T plus and T minus will be fractions and the total of both, that is T plus T minus, will always be equal to unity. Next, we will go for the experimental determination of transport numbers. Here, the first method is Hittorf's method. There are two methods, one is Hittorf's method, the other one is moving boundary method, which we will be seeing in the next session, and in this session we will be seeing Hittorf's method. Now, in an electrolyte, if we place an electrode, and suppose this is an electrolyte, okay. Now, the region around the electrode, there will be changes in concentration, that is due to two factors. One is movement of ions. When ions move, there will be a change in concentration. Second one is the reaction at the electrode. due to some reactions occurring at the electrode, there might be a change in concentration around the electrode. So, what Hitov says is that whenever you have an electrochemical cell where we have an anode and a cathode, suppose this is the anode and this is the cathode. Now, what will be the change in concentrations occurring? Suppose I am taking an electrode which is unattackable, that is, it does not involve any reaction at the electrodes. So, what happens is here around the anode, the ions, they will be moving away from the anode. Moving away from the anode will be, anode is an electrode at which oxidation takes place, that is removal of electrons, and cathode is where reduction takes place. So, those ions which want to get reduced have to move to the cathode. So, what happens is such ions will be moving away from the anode, and around cathode those ions which want to get oxidized will be moving towards the anode, and therefore, there will be a decrease in such ions around the cathode. So, the principle behind Hitov's method is fall in concentration around an electrode is proportional to the speed of the ion that moves away from that electrode. So, at any electrode, the concentration decrease will be proportional to the speed with which the ion moves away from that electrode or going to the opposite electrode. So, we can say specify as speed of cation will be proportional to fall in concentration around anode, because cations are moving towards the cathode, and therefore, there will be a fall in concentration not at the cathode, but at the anode. So, here speed of cation is directly proportional to fall in concentration around the anode, and speed of anion will be proportional to fall in concentration around the cathode. So, that is it, that is those are the ions that are moving away from the electrodes. Now, here we can put this as T plus, that is transference number of a cation is equal to velocity of cation divided by velocity of cation plus anion, which will be equal to fall in concentration around anode, because they will be moving from anode to the cathode, divided by fall in concentration around cathode plus fall in concentration around anode. So, it sum up, you will get the total amount of fall in concentration. Now, after that you can calculate T minus, because T plus T minus is equal to 1, and therefore, T minus can be calculated by subtracting it from 1. So, just determine the transport number of one of the ion, the other ion is determined by subtracting it from 1. Now, here is the apparatus which is used to determine the transport number. We have two vertical tubes, glass tubes. Now, this glass tube has got a stopcock at the bottom, and you have an electrode fused in a glass tube. This is the electrode. On both sides we have electrodes, this is also the electrode. Okay. And this is the anode, and this is the cathode, because it is connected to the positive terminal where there will be deficiency of electrons, and therefore, oxidation takes place here. This is attached to negative terminal where there will be an excess of electrons, and therefore, here reduction will occur, and that is a cathode. So, you have two tubes, one is the anode one and the other one contains the cathode, and these two compartments are known as anodic compartment, and this is the cathodic compartment. Now, so as to prevent the mixing of electrolytes in both the compartments, it should not get mixed. We have a U-shaped tube with two stopcocks at the top and one stopcock at the bottom. Okay. and the connections are made, and this is connected in series to a voltmeter. It can be either a copper voltmeter or a silver voltmeter. This is to measure the total number of equivalents of current passed, which we require in the calculation, and this will be proportional to the total fall in concentration of the electrolytic solution. Now, what we do is, we take almost, suppose you are supposed to find out the transport number of Ag plus ions, you take approximately 0.05 normal silver nitrate solution, and we apply a current of 0.01 amperes to 0.02 amperes for about 1 to 2 hours. Okay. Now, the current is so adjusted, the time of flow of current, so that there is a measurable or appreciable change in anodic and cathodic compartment concentrations, but at the same time there should not be a mixing of the two electrode solutions. That should be taken care of. So, the current is passed with keeping all the stops on the U tube open, not the bottom ones. Of the U tube at the top, you keep it open, you pass the current, and after some time the stop clocks are closed and the anodic solution is drained out. Now, we will go for the calculation one. From the anodic solution, so we have drained out anodic solution, and this anodic solution is titrated against a suitable titrant, and the amount of silver ions present is found out. That is by volumetric method. Okay. Now, we will go for the calculation part. Here, weight of anode solution collected after electrolysis. That is, first we will take the anodic solution from this anode compartment, take it to a previously weighed vessel, and from that we will note the weight of anodic solution, let that be a gram. Weight of silver nitrate present in a gram of electrolyte, let that be b gram, and this is what we obtained from volumetric titration. Okay. So, the weight of solution is a gram and weight of silver nitrate is b gram. So, weight of water present in it is equal to a minus b gram. Okay. Now, we have obtained the mass of water, that is a minus b gram. Now, we have to find out number of equivalents of silver nitrate, which will be equal to number of equivalents of silver plus ions, because silver nitrate contains only one silver ion. Therefore, if I have taken 1 molar silver nitrate, I will have 1 molar Ag plus ions. So, if I get the number of equivalents of silver nitrate, similarly that will be equal to number of equivalents of silver ions. Instead of molarity, if I take equivalence, that will be equal to so much equivalence of silver ions. Now, we have to find out for equivalence of silver nitrate, which will be equal to silver ions present in a minus b gram of water, that is equal to, it contains b gram of silver nitrate divided by, and this is the equivalent mass of silver nitrate. Mass by equivalent mass will give you number of equivalents. Okay. Now, let the number of equivalents of silver nitrate, which is equal to silver ions present in a minus b gram of water, be taken as x, and let the number of equivalents of copper deposited in copper voltammeter during electrolysis, then that will be proportional to the total fall in concentration around the 2 electrodes. Let that be set. So, we are assuming that as a certain alphabets. Now, we are going for two types of electrodes, that is, you can do the electrolysis in the presence of unattackable electrodes. We did not mention what type of electrodes we have taken. If you are going to perform it in with unattackable electrodes, it should be generally platinum electrodes. So, that neither silver or nitrate ions, they interact with a platinum electrode, and therefore, it is done using platinum electrodes. Now, if platinum electrodes are used, there is no involvement of the electrode with the electrolytic solution, and therefore, if the electrode used is platinum and which is not attacked by the ions discharged, you can have two values, that is Y, which is considered as the number of equivalents of Ag plus ions after electrolysis. That is what we have seen in the previous one, that is number of equivalents of Ag plus ions present in A minus B, which is equal to B by 170, which is equal to Y. Okay. Now, X is what? It is the number of equivalents of silver ions before electrolysis. So, these two values when we compare, Y will be less than X if there is no interaction with the electron. Now, fall in concentration around anode will be then, initially it had X minus Y, that is after electrolysis, and transport number of silver ion T plus will be equal to fall in concentration around anode divided by total fall in concentration, and total fall in concentration will be equal to number of equivalents deposited on the copper coulometer, and fall in concentration is X minus Y, and therefore, T plus in this case can be written as X minus Y divided by Z. Then transport number of nitrate can be taken as 1 minus T plus. Okay. Now, if we are using attackable electrodes, that is a case when I am electrolyzing silver electrolyte, that is AgNO3, using silver electrodes. Now, in this case, the nitrate ions will attack the silver electrode and bring silver into solution, and number of silver ions that have been brought into solution will be equal to number of equivalents of current passed, and number of equivalents of current passed is the value we got from the copper coulometer, that is equal to Z. So, Z equivalents of silver get dissolved in this electrolyte. Now, in this case what happens is, after electrolysis you will be getting Y, before electrolysis it will be X. Since X does not contain any silver ions dissolved, but Y will contain the silver ions, that is you will be having Z equivalents extra dissolved in the solution. So, X will be smaller than Y. So, you can't take it as X minus Y. So, what we do is we add the values Z along with X. Y already includes Z, and therefore, X plus Z minus Y will give you the fall in concentration around the anodic compartment, and therefore, T plus can be given as X plus Z minus Y divided by Z, where Z is the total number of equivalents or total fall in concentration, and again T minus is equal to 1 minus T plus. Now, let us go for a problem which is related to this experiment. An aqueous solution of silver nitrate containing 1.2377 gram of salt per 100 gram of solution was electrolyzed between platinum electrodes, and after passing a current for 2 hours, 20 gram of anodic solution contained 0.16 gram of silver nitrate. Mass of copper deposited in the copper voltammeter placed in series was found to be 0.0388. Calculate the transport numbers of silver and nitrate ions in silver nitrate. Equivalent masses of silver nitrate and copper are respectively 170 and 31.77. So, here when we do such problem, there is something to be noted. I will specify that when the problem is done. Now, weight of anodic solution, that is, we are considering the case after electrolysis. Weight of anodic solution was 20 gram. Weight of silver nitrate in that anodic solution is 0.16 gram. Now, weight of water will be 20 minus 0.16 and that will be equal to 19.84 gram, just subtracted. Next, number of equivalents of silver nitrate, which will be equal to number of equivalents of silver present in 19.84 gram of water is, that is, so much of water contained this much of silver nitrate, right. So, this is a mass and you have to convert that into equivalent. 0.16 divided by equivalent mass of silver nitrate, that is 170, and the answer is 0.009412 equivalents. Next, we are going for the before electrolysis part. Now, before electrolysis, we have to be very careful, because before electrolysis, we are having again mass of solution to be 100 gram, weight of solution 100 gram, then it contained the silver nitrate 1.237 gram. Okay. Now, weight of water will be 100 minus 1.2377, that is the mass of silver, and the answer is 98.7623 gram. Now, here the weight of water is 98.7623 gram and so much of water contains this much of silver nitrate. Okay. Here we are having water, that is in 19.84 gram, you are having 0.16 gram. So, both the difference in mass of water, you have to convert it into either one mass, that is, you can either convert it into, there are two possibilities, convert it into 98.723 or you can put it as 19.84, but always it is done in a such a way, that is, we convert this mass before electrolysis to the mass of water after electrolysis, because we are not sure that this much of water may contain proportionally, that is 0.16 proportional to 98.76, because that will not be right, and therefore, always we do the conversion to what the mass of water you have obtained after electrolysis. So, here it is 98.76, which will be converting it to the mass of 19.84. So, 1.2377 gram of silver nitrate is present in 98.7623 into, we have to convert it into 19.84, otherwise we cannot subtract this, and the answer is 0.2486 gram. So, we are converting, this is the important point, we always have to convert the mass of silver present in, silver ions present in mass of water which we have obtained after electrolysis. That conversion is very important, that is the step. Okay. Next, from this we have to calculate, this is the mass of silver nitrate, and this converting it into equivalents, that will be equal to mass of silver ions, and therefore 2486 divided by 170, and you get the answer as 0.001462 equivalents. Now, fall in concentration around anode can be calculated by x minus y, that was what we have been using in the formula. What is x? That is before electrolysis, number of equivalents, this is x, and number of silver ions present after electrolysis, and that is, this is y. Okay. Now, compare these two, you can see x is always greater than y. So, in this case we can directly apply that as x is equal, which is equal to 0.001462 minus 0.0009412, and the answer will be 0.0005208 equivalents. That is a fall in concentration. And mass of copper deposited in copper voltammeter, that was found to be 0.0388. 0.0388. 0.0388 grams. Number of equivalents of copper deposited will be equal to total fall in concentration, and that is equal to mass of copper deposited by, this is the equivalent mass of copper. Which is equal to 0.001221. Now, transport number of Ag plus ions will be equal to x minus y divided by z. Now, what is x? X is number of equivalents of silver nitrate present in the electrolytic solution before electrolysis, and y is, that is equal to, I will put it as 0.00142, and y is, that is the number of equivalents of silver nitrate, which is equal to silver ions in the electrolytic solution after electrolysis, that is equal to 0.0009412. 0.009412. Now, what is Z? Z is total fall in concentration, and that is given by number of equivalents of copper deposited, and that is equal to 0.001221, and by solving you will get the answer equals 0.4265, and this is the transport number of silver ion. To get the transport number of nitrate ion, subtract this value from 1, 4265, and you will get the answer as 0.5735, which is the transport number of nitrate ion. So, this is a way we determine the transport number of cations and anions in the case when we are using an unattackable electrode. Now, let us conclude the session. We have been dealing with the transport numbers or transference numbers of cation and anion. Transference number of T cation T plus is equal to U plus divided by U plus U minus, and that of T minus is equal to U minus divided by U plus U minus, where U stands for the speed of the ion represented by the subscript given there. It is either the cation or the anion, and adding up both the transference number, that is T plus and T minus, gives unity. To determine the transference number, we use a method known as Hittov's method. There is another method which we will be dealing in the next session, and using that you have two expressions. When we are using an unattackable electrode, T plus is equal to x minus y by z, where x is the number of equivalents of that particular ion before electrolysis, y that is after electrolysis, and z is total number of equivalents of current passed or total fall in concentration. When we are using attackable electrode, it should be modified as x plus z minus y divided by z, because in such cases x will be less than y. Okay. Then in both cases T minus can be determined by subtracting it from unity. Thank you.